So we're in chapter 2. Let's jump into it. Hopefully you have clickers ready for today, right? Last time we finished chapter 1 and we emphasized talking about the physical origin of conduction, physical origin of convection, physical origin of thermal radiation, and the appropriate rate equations. All right. I promised some questions. Here's the first clicker question. So the convection coefficient you're told to be is 10 watts per meter squared Kelvin. What is the value of H in units of watts per meter squared? No change there, but degrees C is the change. So now we're up and running. I've got 15 responses. What I'm going to do is I'm going to show you the responses. And you can play around. Okay. So you can play with your clickers a little bit, see how they go. And let's go ahead and zone in on your final answer, and I'll shut it down. I said zone in on your final answer. We're almost there. Come on now, one person. Okay. You're playing with danger there. I've got to end it. One person. Who's got the B? Who wants the wrong answer? Okay, well, fine. That's the correct answer. Thank you very much for participating. It's a difference in temperature. Last time I asked you to think about your thermodynamics class. Think about the notation that you had deeply ingrained into your memory. And so in the thermodynamics class, what was Q used for? The amount of heat transfer. What typical units? Kilojoules or joules. A kilo means nothing. It's just a factor of 10 to the 3, but often it was in kilojoules. What was lowercase q? Lowercase q was specific heat transfer. Just like specific volume, that was volume per unit mass. Specific internal energy per unit mass. Specific enthalpy, lowercase h, enthalpy per unit mass. Specific heat transfer, that's how much heat transfer per unit mass for a closed system. We often did that. Units, kilojoule per kilogram. Professor, sometimes we had an open system, we had mass flow rate through it, and we had heat transfer, the rate of heat transfer coming in. Well, if you took Q dot and divided by M dot, is that any different than Q divided by M? Kilojoules per kilogram. So that lowercase q was a specific heat transfer applicable for closed systems, applicable for open systems. You used it in a lot of throughout the semester. What about Q double prime? I don't remember using it. If it was a very small usage. Maybe they introduced conduction and convection and talked about heat flux. A little bit of it, very little in the introductory sections of the textbook, but it really wasn't used throughout the course. These first two were used heavily. Big Q, lowercase q were used heavily throughout the course. What about Q dot? It was the rate of heat transfer. What units? Kilowatts, which is a kilojoule per second. So we used that a lot. Q dot. Is that the same right here? Is that what I'm talking about? Q dot? Yeah, that's what I'm talking about. What about lowercase q dot? It really wasn't used. I don't remember seeing it a lot. Maybe I saw it once or twice. I don't remember it. Lowercase q dot? No. This class, first chapter, introduced to some syntax, some notation. You want to master it so you don't get lost. When they show you a Q in this textbook, in this class, what is it? It's the same as above. It's the amount of heat transferred. It's the same. That's great. Consistency. I love it. So that's nice. It's the amount of heat transfer And so that's in kilojoules. What's lowercase q? Rate of heat transfer. What would units be on lowercase q? Kilowatts or watts? Hold it. What's this, huh? That's right. Why didn't they stick with, well, different textbooks use different notation. I guess the author didn't want to keep putting a dot on it because the whole class basically is about the rate of heat transfer. What was our laws? Our laws were a flux, heat flux, which is a rate per unit area. So everything seems to be more of a rate. So every time I'd have to put the dot up there, maybe I'll just drop the dot and you know it's per unit time. What about Q double prime? Heat flux. And that was a new concept. We really may have been introduced to it in thermal, but not heavily. It would be kilowatts or watts per meter squared. Right? Isn't that the heat flux? What about Q dot, cap Q with a dot on it? Not used or barely used. What about lowercase q dot? It's not really in chapter 1, but it's in chapter 2. And it's nothing to do with any other q dot before. It's not the rate of heat transfer. It's a volumetric heat source. So you could have so many watts of heat showing up in your energy balance. Your energy balance that focuses on thermal energy, not all forms of energy, just thermal energy, and it shows up in that energy balance maybe because it's converted from electrical by resistive heating. So watts per meter cubed. Last call on homework. Let's go ahead and catch them on the way out if you need to. Thank you very much. All right. So here I typed it out to help you if you need to review this. So what exactly is Q, lowercase q, Q double prime, Q dot, and then in this class, what are they, right? So it's amount. This is what's important here for this class, this semester. I will try to be consistent with the book. I know I sometimes deviate from it, but I try. It's really hard for instructors to be really spot on consistent with a book when they switched and used 4 or 5 different books already. And I've taught at least out of 4 or 5 books, heat transfer. Anyway, so joules or kilojoules, watts per meter squared, really not used. And this volumetric source, sometimes I'll tuck a SRC on it with a dot to be consistent, but really this is a source, a heat source, a volumetric heat source showing up in our energy balance equation. True or false, clicker question, answer A for true or B for false. In order to have a heat transfer, there must be a temperature difference. Select answer A for true or B for false. In order to have a heat transfer, there must be a temperature difference. We'll stop this at 20 seconds. So we'll go ahead and stop. Where's my stop button? Hit the multiple choice again? Really? I thought they gave me a stop button. Square. So there it is. Congratulations. Somebody really likes B. Check your heat never flows from cold to hot. A is true, B is false. Heat never flows from cold to hot. True or false? All right, I'm going to go ahead and stop it. So now we'll go ahead and show the result. And More people got stuck on B. Heat will never flow from cold to hot. In the way that we're talking about heat, we're talking about heat transfer, conduction, convection, radiation. It would be a violation, you can apply the second law and see it, that it violates the second law for somehow two things at different temperature, one hot, one cold. You put them in thermal contact, allow a heat transfer, and one gets colder and one gets hotter. That would be great. You could make $1 million. More than $1 million. Yeah, why stop at $1 million? Go for $1 billion. But it's not going to work. Heat flows from hot to cold. Professor, how do we get refrigeration systems? Well, what you're doing is you're pounding on that refrigerant, beating it up to boost its temperature so you can dump heat to something that's less cold than it is, the refrigerant. True? The outside of the hot day. But you put it through a compressor to achieve that. And then when you put it through the expansion valve, it drops the pressure. All of a sudden it's cold. The fluid in the evaporator is really cold compared to the air blowing over it. Again, heat flows from warmer to colder. It's a clever engineer that pumps water uphill and moves heat from something cold to hot. All right. But it doesn't come naturally. All right. What symbol is used for the thermal conductivity in this textbook? Lowercase k. What other symbols used throughout the world? Probably the majority of the world, lambda. But that's okay, it's not used in this book. But I'll show an illustration where they put lambda and you shouldn't be too confused. Like, what's lambda? Well, it's the thermal conductivity. What are the SI units associated with the thermal conductivity? 20 seconds. Answer A, B, C, D, or E, dimensionless. And we'll take a look at the results. And very good. What is the common mistake? What would be the most common wrong answer? C. C. C would be the most common wrong answer. We'd reviewed convection. What a symbol is used for the convection coefficient in this textbook? H. What is the SI unit associated with the convection coefficient? All right, we ready to close it out? Let's go ahead and close it out. And we show the results. Congratulations. C, watts per meter squared Kelvin. Got it? Very good. And what symbol is used in radiative heat transfer? The emissivity. That's a epsilon. Epsilon. What are the SI units associated with the emissivity? I'm closing it out. And we'll show the results. It's dimensionless, is it not? So the emissivity is dimensionless. It's a range. Can you have an emissivity of 1.3? No, it's between 0 and 1. 0 and 1 is the emissivity. So now we move into chapter 2. The topics, it doesn't look to be a very difficult chapter when you look at the outline. Hey, introduction to conduction. Well, we're going to go back and review the conduction rate equation, generalize it. We already introduced to the conduction rate equation. What was the name of the conduction rate equation that we were introduced to in chapter 1? Fourier's law. That's exactly right. But we're going to generalize it from 1D rectangular to multi-dimensions, 2 and 3D. Then we'll take a look at the key property in Fourier's law, the property associated with what material you're conducting heat through. That property is known as with the symbol K or lambda, the material property known as the thermal conductivity. We need to talk about thermal conductivity. We have a lot of different materials, gases, liquids, solids. When do we expect it to be high? When do we expect it to be low? Maybe why is it high for metals? Why is it low for non-metal solids? Then we put them into what we call the heat diffusion equation. So heat can be transferred through the material. And if we wanted to predict the temperature distribution in the material, we'd probably write the heat diffusion equation. It would be what they call a PDE mathematically. What's a PDE? Partial differential equation. that then you could solve to get the temperature at any location in our material, get the temperature distribution. Well, not just the PDE, which is a representation of the conservation of energy inside that material, where energy flows through the material by conduction, but you also need BCs and ICs in order to have a complete mathematical problem, and so that you can apply your mathematical skills to solve for the temperature anywhere. What is BC? Boundary conditions needed for that PDE. IC? Initial conditions. So the last half of this chapter is very mathematical. Just very rigorous mathematical. Okay? What is another name for the conduction rate equation? The conduction rate equation. What is another name? Is it known as the first law of thermodynamics, the second law of thermodynamics, Fourier's law, Newton's law, or the Stefan-Boltzmann law? All right, everybody in? No. Hey, no, you have to answer. Come on, it's not time to... It's just, I just talked about it. Off and kaboom. See, 96% of the class was listening. Didn't we just talk about it? So you say, why didn't they just say the beginning section of chapter 2 is Fourier's law? I don't know. They said it's the conduction rate equation. What's the radiation rate equation? Stefan-Boltzmann law. What's the convection rate equation? Newton's law of cooling. But hey, it's the rate equation. It helps you not predict the amount of heat transfer, but the rate of heat transfer. That's why they call it the rate equation. So Fourier's law we were introduced to, and we had Q double prime equal to minus K dt dx. True? What was T? We think about it as a function of location, one-dimensional rectilinear in the coordinate system X. That's a temperature distribution. We reviewed that last time. Then we had dt dx. What was the name of dt dx? That was our gradient, right? That tells us the slope. And because of the negative sign, it goes down from high temperature to low temperature. That's the direction of heat flow. And this constant of proportionality, known as the thermal conductivity of the material. So this gives us the heat flux. Well, what is a generalization of this gradient in multi-dimensions? Move it to 2 and 3 dimensions. You would say not the rate of change of temperature with respect to x, but you would say the gradient of temperature. Thinking about temperature maybe as a function of location x, y, z, if you're three-dimensional rectilinear, or r theta z, or rho theta phi. So all three coordinate systems: rectangular, cylindrical, and spherical. But what is this gradient? Well, you have to just remember. Isn't this the grad? This is the gradient, del, that you were exposed to in your math classes? Yes, it was. So it's the rate of change of temperature with respect to x in the I, the rate of change of temperature with respect to y in the j, and the rate of change of temperature with respect to z in the k. Couple subtle things. What's I, j, k? Unit vectors in the principal coordinate directions. The x-axis, along the y-axis, z-axis. Why do they have this, this funny derivative like this instead of this other derivative? Are you getting lazy, Professor, on the writing the d for the derivative? It's a partial derivative instead of an ordinary derivative. So we understand all the terms in that gradient operator. True? So what you can do is you can write Fourier's law in 3D or in anything really. You can write it in the general vector notation. Q double prime with the vector on it is equal to minus K gradient of T. Because when you take the gradient of a scalar field, this is a scalar, won't you get back the result a vector field? Isn't that a vector with the I and the j and the k? Yeah, it's a vector. I took the gradient of the temperature, I got back a vector. That vector is the gradient of the temperature field. I multiply that vector field by K, the thermal conductivity, put a negative sign in front of it, and I have another vector field called heat flux. This heat flux is a vector field. What does it mean to be a field? At every point in my domain, I could go there and inquire and say, give me the temperature. That's a numeric value with units. That would be like a scalar field. I could go to that same point in that solid, in that domain, and I could say, give me the heat flux. It would say, okay, here's a vector. I'm going to show you which direction it's going, and I'm going to, by the vector, it's going to tell you the rate at which it's being transferred per unit area in that direction. That's what the heat flux vector field is. Oh, man, too many questions. I'll ask this one right here. Temperature gradient is represented by either a scalar field or a vector field. The temperature gradient is represented by either a scalar field or a vector field. Everybody in? Okay, let's close it out. This is one of these challenging things. Temperature, if I said, go to this location in a domain, give me back the temperature, you'd report maybe 25 degrees C, a number with associated units, but it wouldn't be a vector, would it? So anywhere in the domain X, Y, and Z, I'd give you back a scalar. It's called a scalar field. But as soon as I do this to that scalar field, I get an entity called a vector field. That's a vector field. And then you multiply that by minus K, and you still have a vector field, but it's very meaningful to us. This vector field means something about if I move in this direction, I'm telling you how fast it's changing temperature. Actually, it shows you the direction of the max and the rate of maximum change of temperature. The direction and rate of the maximum change in temperature. Here, this shows you the direction and rate of heat transfer per unit area, or heat flux. That's what it's showing you. This is grabbed off the internet somewhere. So I'm trying to introduce this concept of temperature field, which is a scalar field. So you introduce a grid. Here's a distance of 1 meter, then 2 meters, then 3. You could say this distance is 1 meter, 2 meter, 3 meter, 4 meter, and the X, and also in the Y. And then at every point here on the grid, I say, tell me the temperature. Oh, it's 19 degrees C here. Oh, it's 21 degrees C here. It's 24 degrees C. It's 25 degrees C. So those values right below the points tell me the temperature at the points. True? So instead of showing the temperature everywhere, I just show it at key points called a grid. That's common in engineering. So this is a temperature field. It's a scalar field. Mathematically, we call it a scalar field. Which temperature field, for that same one I just showed you, is correctly drawn isotherms? Version A, version B, version C, or version D? Drawn isotherms. Which map of these A, B, C, or D, 3 of them are wrong, 1 of them is correct, is a correct representation of isotherms? Professor, what are the isotherms? Those are the lines. This line is an isotherm. That's what they're showing by a line, right? Okay, is everybody in? All right, I'm going to go ahead and shut it down. Now I ask the question, who voted for D? Who would like to explain why D is the correct answer and not A, B, or C? Back there.
If you look at the isotherms,
right?
they intersect the same temperature point. Like each point that they intersect is exactly the same.
That's right. So you could trace this one right here. It goes 22. It goes 22. It goes 22. It goes 22. And between 23 and 21, I know somewhere there's 22. So all along that line is 22 degrees. Is that true maybe for this line right here? No, not at all. Or this line over here. So D is correct, isn't it? That's what an isotherm is. Now that we have the concept of isotherms, then think about, I would say, I want you to visually talk about the gradient of T. I know I can evaluate that everywhere, but we typically evaluate it where it's convenient to evaluate it, maybe at a grid, right? So what would it look like at this point right there? What would the gradient of T look like at that point? Okay, you're helping. I think you got it. What did you say?
The vector would be pointing towards the fastest approach to the highest temperature, which is in the upper right corner. And then it would have a certain magnitude in that direction.
And it would have the magnitude. And one word I'm looking for, perpendicular to the isotherm. It's perpendicular. So right away, he says, go and search along this line, which is perpendicular to the isotherm at that point. And I know that the gradient of T is pointed in one of those two directions, either to the north, what is that, northeast or southwest, right? Okay, so it's either pointed in this direction, clicker question, A, or it's pointed in this direction, B, but I know it's along that line. Is it A or is it B? Clicker question. The gradient of T. That's the only thing we're talking about right now. All right, everybody in? One of the things you probably learned before is if I have a generic scalar field f and I take the gradient of f and then I dot it with a direction vector n, which is normal length, that'll tell me the rate of change of that f in that direction n. That's what the purpose is, right? So if I dot it in the same direction that it's pointing, then I get the maximum of that answer, which is the maximum rate of change. And if I had two vectors, here, if I put the gradient of f like this and I put n like this, then I'll get a positive answer. If I put the gradient of f like this and then I put n like this, what do I get? Just the opposite. I get a large negative number, right? Right? And if I put the gradient of f like this, come on, I can write gradient of f, and I put perpendicular to it, n, what answer do I get for the dot product of the gradient of f and n if they're perpendicular? 0. Well, professor, how about if I try this side? It's still 0, right? So it goes from large positive to large negative. What's the large positive? It's the rate of change in that direction, and the negative is the same magnitude, but it's negative because it's changing in the opposite direction. Instead of going uphill, you're going downhill. So basically the answer is, for this one right here, it's in the direction of maximum increase. Isn't that the gradient? Isn't that the gradient of the T? So if I move from 24 and I move this direction, I'll be increasing the temperature, and it tells me the rate at which as I move. So it's the units on this are what is how many degrees C change per meter or per inch or per foot, whatever my length scale is. Okay, that's all great, but we're interested in heat flux. Well, the heat flux is Q vector double prime is equal to minus K gradient of T. So for those that had the wrong answer, A, for the previous problem, hold it, A was correct for this previous question. Let's go ahead and grade it. A was correct, true? But did you know that for the next question, which is the direction for Q double prime, then B would be correct? True? So one goes in one direction, the other in the other. So now plants, now I don't have time. I was going to give you a chance to catch up, those that missed it, but sorry. It's A, it's in that direction. But that's the gradient of T. And what is this direction? This is the Q vector double prime, the heat flux. Okay, now if I look at this point And I'm going to call this point, I already called it a point, let's call it point A. And I come up and I look at this point right here, B. This is point B now, right there. Point B, can you tell me where is draw the heat flux vector. What does it look like? Is it going this way or that way? The first or the second? The first. You're catching on. This is great. Now this is really challenging. I hate to ask it. But I'm going to compare the rate of change. We got the direction right. But the rate of change, the magnitude of the heat flux for the point A or the point B. They're not in the same direction, true. We know that point A is moving in this direction, but I want to talk about the magnitude now. Which one has a greater magnitude? A or B? And give it your best shot. I know it's a challenging question. Everybody in? Please, I encourage you to do what a lot of students have done already. Sit next to somebody and talk. And if you're lost in a class, talk about the football game, basketball game. I don't care, but talk. How's that? It's better than sitting alone. And then every now and then you may drift into, like, what class are we in? Yeah, okay. No, then you may have some relevant discussion. But make a friend in the class and talk to them. And I need to stop that and degrade that. I need to stop it, right? So which one is correct? The B is correct. Why is B correct? Because it's not going to have to travel as far before it hits the next isotherm. So this one is it's going to take a while before you get to the next isotherm from 24 to 22. That's going down the temperature. That's the direction of the heat flux. But this one's going to hit it pretty rapidly. So you know that the rate of change is more dramatic there. The isotherms are tighter together. They're tighter together up at B. All right. Maybe that wasn't a great question for you. Sorry if you missed it. Let's continue on. I was going to use this larger plot to make it more visible, but I didn't. How about this? How about the vector for the heat flux right at this point is going to be perpendicular in that direction, right? And forget it. I'm done with this. Okay, I already asked this question. Leave it alone. Now we're going to talk about that important property known as the thermal conductivity. We already know its units, and we know it depends on the material. But first, could it be isotropic, or could the thermal conductivity be represented for an anisotropic material? Well, anisotropic materials do exist, but they're beyond the scope of this introductory class. And so when we talk about isotropic materials, that means that the conductivity doesn't change depending on what direction you're trying to go in the material. But if you have a composite, and the composite material has embedded strands, and there's a whole bunch of them, and they're pretty high conductivity, and they're glued together with some matrix material which has low conductivity, then you know it's going to have a preferential higher thermal conductivity of the effective bulk of the material in that direction compared to that direction. That would be anisotropic, not isotropic. So you're exposed to the possibility and the reality that there are materials that have properties which are directionally dependent. But if I talk about aluminum or copper, it's isotropic. If I talk about water, isotropic. If I talk about air, there's no directional dependence, it's isotropic. Let's take a look at the relative magnitudes. So the thermal conductivity of a gas is less than of a liquid, and the solids have the highest. So this has the highest thermal conductivity, the lowest thermal conductivity. So here on this x-axis, you can see the thermal conductivity. They used the symbol lambda for the property, thermal conductivity. It has the right units, watts per meter K. We know it's a thermal conductivity just looking at the units. And you can see the range. Let's take a look. What is the x-axis scale? Is that a log scale? It's a log scale. So you go from 1 to 10 to 100 to 1,000. That's a dramatic change. You're packing a lot of range of values in. Let's just throw pure metals, and you have copper as a benchmark. What's the value of K of copper? That's a really good conducting material, copper. Pretty hard to beat. Oh, you can beat it. But it costs a lot to buy copper, and probably to beat it, you're going to pay a lot more money of something else. As an engineer, you think about money. So what is the value of thermal conductivity of copper, roughly? 300, 400, 500 maybe? But it's log scale. 6 is probably pushing it, but about 400 or 500, right? How about ice? Solid water, ice. 4 watts. That's 100 less than copper, isn't it? That's a big difference. How about liquid water versus ice? Liquid water. 0.8, 0.9, a little less than 1. Thermal conductivity. It's still pretty good for a liquid, but it's a lot less than some of the solids. How about for air? 0.03, 0.02. Significantly lower. So gases, you could tell, low, solids high. Somebody says, I got a material that's conductivity is 5,000 watts per meter degree C. What do you think? You're blowing smoke somewhere. You know, it's not going to work. Or they say it's 5 times 10 to the minus 6. No, it's just not there. Okay? So these are the type of questions, if you ever want to get a doctorate in mechanical engineering, that sometimes they torture students with that are sitting there for the doctoral qualifying exam. 3 faculty, and they ask a question, and you say, "What? Give me a typical value of thermal conductivity for blah blah blah." I don't know. Guess. No, you have to throw out a number. 5,000. Ha! He said 5,000. Ha ha! The whole room erupts. Whole room erupts in laughter, because you didn't know roughly the range of values. I'm not saying memorize this, but hopefully you get the values down. Now, there's 2 big mechanisms. This was lost in the translation for heat diffusion in solids. One is the same transport mechanism for electric flow in solids. So in metals, if you have a good electric conductor in a metal, high electric conductivity, you have a high thermal conductivity because the flow of free electrons carries with it a lot of heat. And so they're showing you, hey, copper and all these sort of line up as you increase, the conductivity increases. Electric conductivity goes up, thermal conductivity goes up. The other is solids are often in what they call a lattice. They're related to each other. And I know there could be very amorphous, but a lot of times they're organized in relationship. And those lattices start to jiggle. They get waves in them. You can describe waves by some wavelength, or just like electromagnetic, you can describe packets. Packets of energy, of waves flowing through the system of a lattice, vibrating. Those are called phonons. There's your new vocabulary for today. So electrons or phonons carrying. What are the phonons? Vibration of the lattice of the material. What happens if it's amorphous? It's not very good at conducting compared to if it had a lot of structure to it. So what's going to be some of the best? Very crystalline with a lot of free electrons. So very expensive, what do they call that? Diamonds. Diamonds. Very good. Very high. But, all right. So the non-metallic solids drop because you lose that conductivity associated with free electron flow. And so right away, plastics and ice, they're not very good at conducting electricity. They're not as good at conducting thermal heat transfer as well. So it drops. But they're still typically better than a lot of the liquids, and definitely some of the insulators, which are primarily stagnant air. Now let's compare the fluids. Here's air. What type of fluid is air? Gas. How about ammonia vapor? Gas. Steam, gas. CO2, gas. What is this? Liquid water. This is ethylene glycol. Do you own any? Is it in your radiator? Probably. So ethylene glycol. So that's liquids. Engine oil, liquids. So these are liquid, liquid, liquid. But here you have. So what's the trend? Liquids have higher thermal conductivity than gases by a significant amount. Also, there's a few anomalies in this. What are these two gases? Hydrogen. How does hydrogen float around in this world? As H or H2? H2. What's the molar mass of diatomic hydrogen? 2 kilograms per kilomole. How does helium float around in this world? Monoatomic helium or diatomic helium or triatomic helium? How does it float around? Monoatomic. What's the molar mass of helium? 4. All right. Compared to air, 29 for molar mass. Ammonia, I know it's not that high. NH3, ammonia is NH3. How much for the nitrogen? 14. 1 for each of the hydrogen. So it floats around as 17. What about carbon dioxide? It floats around with a molar mass of 44. Carbon with 2 oxygen. Steam is 18. Anyway, they're heavier. The heavier the molecule of gas, the lower its thermal conductivity. Why? Smaller mean free path. Those small molecules really go a long time and then they bump into somebody else. And so they effectively transfer heat over larger distances because of the mean free path.
Does a water line?
Yeah. So I'm trying to not rush, but rush. How's that? Material conductivity can be a function of temperature. This is going from 0 out to 1,000 degrees C. So silver, copper, aluminum, they vary as a function of temperature, but it could be more dramatic than it is. As an engineer, get the right temperature. If you have a problem where it's between 400 and 600 degrees C, evaluate the thermal conductivity of aluminum at 500, and you're going to do well. All right? Okay. So thermal conductivity, I'm going to end with this one, is a property of the material. What does it measure? It measures how readily heat passes through the material. If I have a high thermal conductivity, for the same temperature gradient, I'm going to have a higher heat flux, aren't I? So it can be read as the heat flux per 1 degree C per meter temperature gradient. Or in other words, I take the law, Fourier's law, Qx double prime equal to minus K dt dx, and I just say K is equal to what is my heat flux in that direction divided by the magnitude of the temperature gradient adjusting for the minus sign. Let me finish. There's another property, thermal diffusivity. Alpha is the symbol given for it. It's defined as the ratio of K, thermal conductivity, divided by rho and specific heat. It's a measure of the property of the material. But it indicates how readily heat passes through the material and heats it up. So if K is high and rho C is low, it easily passes it and it readily heats up. If K is low and rho C is high, it doesn't pass it very well, and it takes a lot of heat to boost the temperature, to change the temperature. It takes a lot to heat it up. So it's a comparison of conductivity and volumetric heat capacity, thermal diffusivity. It's just another material property. You had a question?
Yeah, I was saying, could you explain that again on conductivity?
Yeah, let me answer that question right after I close out because it's more one-on-one. So thank you for your attention. We'll see you next time.